Thanks, Sydney, and thanks also the whole HPC Advisory Council team here for having organized this really fantastic sessions. I learned a lot and I profit pretty much from my stay here. It's really great. So so my talk is a little bit again to introduce a little bit our work that we are doing inside NVIDIA, and of course we continue still to be the high performance, the high performance computing branch, and so this is still very, very important for us. AI and deep learning we started about 5 years ago, so we have tons of libraries, tons of applications, and today we see that we have been right, or that Jensen has been right in predicting that AI would be the future revolution. And we also started today with the data analytics. So not only we can now do AI and deep learning here, but we also provide solution now here for really machine learning, boosted gradient, and data analytics for graph analysis, for example. Okay, and orthogonal approach to Frederico's CUDA, we have a virtual desktop interface that runs on the VMware and the Citrixes of the world, so we can virtualize here GPUs and share them via the virtual GPU interface. Okay, so this is a little bit how we are doing. We have, of course, the whole stack well, from the application side, of course, we have all here. From the AI segment, we have speech and translation and so on, you name it. We have also now a very in-depth investigation in the healthcare with the Clara project, and so we are working also a lot with healthcare here and doing this image analysis. And healthcare typically has very, very big images, a little bit of a problem to bring them onto the GPU. And then, of course, we have the traditional HPC segments like weather forecasting that we have already seen this morning, and so on. So, okay, so these are the application domains. In between, we have all these already ported applications, like, for example, all the frameworks. They run naturally on GPU, but of course, the quantum chemistry and the molecular chemistry, VASP, GROMACS. We have Dassault, Simulia, and so on and so on. So we're a total of over 500 or even more applications that are already ported. When you look up the GPU applications catalog, you can find them rather easily and pick up the one that you would need. Over the already ported applications, we have the libraries. Of course, in HPC is known the CUTLASS, QFFT, random, and so on and so on. We have some specialized libraries for deep learning. That is the CUDA deep neural network, cuDNN, that is used to train the networks. However, when it comes to deployment, then you would use TensorRT or DeepStream. Okay, so this is a little bit the different things. PGI is, of course, also here on the product side, because you can compile for the GPUs by using the PGI compiler. And of course, underneath we work with all the OEMs, the Hewlett-Packard and so on, IBM. It is so we work with all of them. And of course, we are more and more prominent on the cloud. But we already had some very good discussions here yesterday that cloud is yet an expensive and perhaps for HPC not feasible thing to do. Okay, so this is a little bit what our stack looks like. In June, we announced that we actually provided with IBM the biggest system, well, top one of in the 500 list, and this one here is 122 petaflops when you run LINPACK. Okay, so we are number one with this number. But you can also do some genetic analysis, and you will use deep learning, and by using all, because the GPUs will not come only with the CUDA cores, but with also what we call tensor cores. I will come in more detail on this a little bit later. And if you use all the possible processing power that is on the machine, then you already reach today an exaflop, or even 3 exaflops here. Okay, so the exaflop computing is possible when you use the hardware that is provided by a GPU, meaning tensor cores and so on. Okay, and so the Summit has a total of 27,000 GPUs, and Volta tensor cores, pardon. And so it's huge number. And not only Summit, but of course we have also the Sierra, that is the second, and so on and so on. And we are very interested, of course, in the positioning not only on the top 500 list, but also in the Greenest, on the green top 500, because this really shows how energy efficient we are. And energy efficiency is definitely a way on how to get the exaflop. You have to be energy efficient in the solutions. Here we see the Volta that is on that is really the working horse in all these platforms. And so what we have here is the SXM2 format. The SXM2 format is just like a small credit card, and the chip actually is here. The memory, the high bandwidth memory is here. You get a 900 gigabytes per second high bandwidth memory. In this format, it comes with 6 NVLinks, 6 links as a dedicated GPU bus. Okay, and so with these links you can connect other GPUs. That is nicely shown here. So here we have 4 and 4 GPUs, and then they are connected with these 6 links among each other. Okay, so we get some dedicated GPU interconnect. Of course, this processor runs at 7.8 teraflops double precision. This is what you need for LINPACK, so we are very good at this. However, it has 125 tensor teraflops for mixed precision. Okay, and this is really now crucial to use, or these resources are crucial to use, because they are dedicated hardware that you can actually use to do the computation. And of course we have here, or we also continue, of course, the co-design that we have done happily with Mellanox here, for example, the GPU Direct and the GPU Direct RDMA that allows you to bypass the CPU and directly write into the remote memory of a GPU that is on a different node. Okay, and in this way we can scale multi-node very easily. The latest announcement here now was also now the Tesla was the Turing. Okay, so Turing was announced I think in May, and here it's already a much smaller form factor. It is much less power consumption. Okay, and here, this one here is really thought to be an inference solution. Okay, inference means once you have trained the networks, you're gonna deploy them, and a lot of customers are looking to deploy deep learning, and when you want to do this, then the Turing is an ideal solution. And now we come back to a little bit the different DGX stations and so on. The entry level hasn't changed, so this is the DGX station that goes under the desktop. It is very silent because it is liquid cooled. Okay, it comes with 4 Voltas, SXM2, and so this is a entry point. And then we have the normal DGX1 already out for a while, and here in the DGX1 we have not 4 but 8 GPUs, and then they are connected here in this hypercube switching structure. And this is a little bit how it looks like. This comes with 2 Intel CPUs. The CPUs must be very, very powerful, so we hand select the dual Xeon CPUs because GPUs, to keep them busy, draw a lot of data, draw a lot of things, and so on and so on. So you cannot use any CPU that is available. Okay, so now we had 4 for the DGX station, 8 in the DGX1. So what will be next? Right, so 16 now, okay? So 4, 8, and now we have 16. And 16 is called the DGX2. And here we see 2 drawers. So it's a two drawers. So we have 8 here and 8 underneath. Okay. In order to connect them, we developed the NVSwitch. NVSwitch is based on the same technology as the NVLink. And so we can get a direct-to-direct communication link by using the NVSwitch. And this gives a total of 2.4 terabyte bisection bandwidth. This machine has a huge bisection bandwidth. It was already discussed or mentioned before. So we get unified memory now for the GPUs. So here, using unified memory for the GPUs, of course, every Volta comes with 32 gigabytes. But now we see 16 times 32 gigabytes, and we can access this from each CPU via the switch to any other GPU in the way that we want. Okay, so this one is a very powerful machine, and it is thought to be to solve all the problems that are needed to be solved in memory. Okay, and in memory means also, for example, for this machine learning, deep learning is perhaps. But machine learning definitely on all graph analytics and all these things, they can run now here natively in memory. And here is also one idea that really started as some idea of some colleagues. And they thought, okay, what would happen? Because normally we draw 350 watts as usual, okay? However, when you produce the GPUs, we can sometimes get certain SKUs that support higher voltages. Okay, so instead of drawing 350 watts, sometimes we have GPUs that are able to run at 450 watts. So we hand selected them, these 450 watts, and put them in the DGX2. So put them into this system here, and then we stuck them. Okay, and so we had, I think, 96 or something like this. So 96 DGX2s, and we stuck them in a rack and run them at 450 watts. You run LinPack on it, and you are on number 22 in the top 500 list. Okay, and so this is a very encouraging. Yeah, here 96 DGX, and then of course we were so excited about this that we gave it even a product name. So now this is called DGX2H, and so with the DGX2H you can get very, very powerful solution, and it is connected of course with the InfiniBand Mellanox EDR, and this gives absolutely great performance. Okay, so now I just wanted to discuss a little bit one project, as we have the direct, the GPU direct, going then from one GPU directly on another node to another. We're also now looking for a similar approach here for the GPU direct storage. So here the idea is to combine that the GPU have a direct memory access, a direct disk access, a direct disk access, meaning bypassing the GPU, the CPU. And this project is still in exploration. If you are interested in this, if you know customers who could be possibly interested in the solution, please let us know or let me know, and we can then try to collaborate on this one here. And the idea is to have from the application to have a CUDA file API running CUDA, and then of course here in our driver we will do the modifications that are necessary. Yeah, and this is the blog that is mentioning this. Okay, so now so Volta was already using the tensor cores, and here Turing uses them even more. Turing comes also with integer 8, integer 4 and binary tensor cores, so there's a lot of possible usage of these tensor cores that can be done. And here is a way of how they are really working. So they are working on a 4x4x4 matrices or processing arrays that are done then on a single clock. And so they compute in 16-bit half precision, they compute the matrix multiply. However, you can accumulate then, of course, in 32-bit. Okay, so this is the basic idea of these TensorRT cores. And you can also call it directly from this warp interface and warp level matrix operations in CUDA C++. And here you will see that you can define the matrix ABC, and then you just call here the MMA sync. So from this new interface you can easily call it. Okay, so this is possible also to hand code the calls then to the tensor cores. When you do this, of course you get you can, or the groups that have already implemented this are here the Plasma Fusion from Oak Ridge, implementing the solver in FP16. We have here earthquake simulation from a Japanese group, and we also have here the weather simulation, so hurricane trajectory prediction here from Oxford. And here the idea is, of course, to have everything or a lot of things implemented in 16 in the tensor cores. It runs much faster, and it stays, as you may expect for the weather codes, in a certain error range that is still acceptable. It stays within 5%. Okay. And also one suggestion was from Jacques Dongara. So here's a publication investigating precision arithmetic to accelerate dense linear systems. And so here, when you do a normal LU decomposition, you try to solve AX equals B with a normal LU decomposition. So normally you run here at a maximum of something like 4 teraflops, and for big matrix sizes. However, what you can do is you can compute an initial solution here in half precision in FP16, and then have some iterative algorithm on it to refine it. And in this case, you run here at 26 teraflops. Okay. And the device is, as I already mentioned, 7.8 teraflops. Okay, so you're using much more than the device can deliver with a standard LinPack. Okay, so these are a little bit the ideas that are behind the tensor cores. Now let me introduce a little bit OpenACC, and so Peter yesterday already gave a nice presentation about OpenACC and showing a little bit where we are today. So today we can use OpenACC as a very easy starting point for example, students or people who are interested to have a quick port of the code done. Okay, so here, for example, the ACC kernels is a hint to the compiler to find himself the parallelization of the loops. Okay, we do not impose nothing. Of course, we can also do the traditional OMP style, where we will precede every loop with the corresponding directives. So both are possible. Okay, so here, for example, then we can compile for the MULTICORE, we can compile for Tesla, you can compile for IBM. It is really, really wonderful to have a single source code running on all these different platforms. It is also available, of course, in GCC. And you have tons of these. You have hackathons, you have information sites, and so on and so on. So really a lot of activity, growing activity, of course, around OpenACC. And the PGI compiler, the latest version is 1901, so January in 1990. And so they are supporting also the tensor core, so you can program the tensor cores. They had the full 77 language, OpenACC 2.6, OpenMP 4.5, and so on and so on. So a lot of things that are new. Here's, for example, so there's also one possibility now with the PGI compiler to see the differences between CPU and GPU. So when you have some results that you're 100% confident in, so you set your baseline, and then you can see if the results of the GPU or the accelerator under consideration will diverge or not. Okay, so this is also this is the PCAS tool that is available now for the compiler. I already mentioned C++ 17, so everything should be there, threads, PSTL, and so on. So this is for the C++ guys. And of course we still continue legacy Fortran, okay. Array syntax will be now implemented in Fortran 90. You will have the Fortran for all statements from Fortran 95. Co-arrays will finally be doable now. And then we have, of course, the do concurrent statement. Oops. So all these are possible. The PGI compiler in the community edition is free, okay. So if you are a university, you can just download it and use it, okay? So this is really fantastic news, okay? The only thing is, of course, you don't get too much bug support, so you have 1 or 2 updates a year, that's all, okay? So when you need a professional solution, of course, you can subscribe the professional edition or even the enterprise edition, okay? But the community edition is free to use for everybody. Now let me look a little bit at the different CUDA things. So yeah, so CUDA 10 is the latest version that is out, and here we see now the QFFT running on the big DGX2 systems, and we see linear scaling for the different sizes. So this is one here by 1024, a 3D complex convolution, FFT, sorry. And so this is very interesting to follow, and there have been also very interesting talks here on GTC. QSolver has updated now the symmetric eigensolver. So this one here is now updated. We have one library that is called CUTLASS, and that implements the CUBLAS, if you want, in the tensor cores. Okay, so you can call, instead of calling CUBLAS, you call CUTLASS, and it will do the same thing at that CUBLAS is doing. And finally, the only thing that is new for QSPARS is that we can now, the only thing that is missing here for QSPARS is the sparse matrix multiplication. Everything else is complete. And it's performing, of course, very well. The NSIGHT products family got completely updated, so debugger, profiler, and all these development tools, they are really good to use. And so here we have now, for the deep learning SDK, so we have Nickel 2, and Nickel 2, well, it was already said that for whenever you want to train a network, then you have to compute a gradient, and then you have to, at the end, you will have to go a global reduction, okay, or a global communication. And if you're using a NICLAS is exactly implementing all these reduction or all these global communication functions, these reduction functions that we know from MPI. They have exactly the same syntax as MPI. MPI all reduce, MPI gather, and so on and so on. But they run here on the NVLink, okay? And you will have to use this kind of library if you want to do deep learning, for example, if you want to compute the gradient. And they run here in the latest version in NICL 2, also in multi-node. And NICL will always try to find rings, so NICL will analyze automatically when you kick off NICL. It will try to find the optimal configuration for all GPUs participating here in the communication. I already mentioned that when you come to deployment, the requirements are very different than from training. Training, you prepare yourself for hours and hours and hours. Deployment has to be is completely latency bound. Users are not willing, or not only users, but sometimes also the technical requirements make constraints to have nearly real-time decisions on nearly real-time things going on, okay? And so this is the idea of TensorRT, and TensorRT is really an inference engine that optimizes the trained network at every level, fusing layers, fusing kernels, all the things that you can do in HPC when you have access to a code, and then you can just deploy it, okay? And you can give it a special target, you can run it for certain batch sizes, and so on and so on. So the TensorRT is very good. And also we have now direct plugins because TensorFlow is pretty much used. So we have direct plugins from TensorRT into TensorFlow. And I already mentioned Rapids, the machine learning library. Also very important for us is to touch somehow the whole machine learning community, and that is not necessarily the deep learning community. And here we provide, so based on this Apache Arrow format, so we have, it is all in-memory databases or in-memory processing, okay? So everything is pushed into the GPU, and then you can treat it in the GPU. And here we have the CUDA data frames. So for the analytics, we have the machine learning interface, that is QML. We have QGraph, I already mentioned, for the big graph analysis. So you dive into the graphs. Deep learning we know, and QXFilter for visualization, okay? And the rough roadmap. So today we have already the XGBoost that was already announced at the beginning. However, here we have a lot of other candidates. Stochastic gradient descent, ordinary least squares, Kalman filters, uniform manifold, and so on. Somehow is also density, so this is dbScan, and so on. Yeah, here's it. So the k nearest neighbor, and so on and so on, okay? And we work on this with a certain priority, what we think is necessary for the customers. However, if you have one customer, or if you have one research group that would like to have one of these algorithms, or even another one that is not yet even on the list, to run on the GPUs, then please contact us, and we can always try to influence all these different porting issues or decisions. NGC now, just before finishing, everything that we can think of is pushed to NGC. NGC is the NVIDIA GPU cloud, but it is not. It's not a computing cloud. Okay, you cannot compute on our cloud. It is only a container repository. Okay. Every idea that we have, we package it as a container, as a Docker container, and of course you can run it also under Singularity. You are not constrained to use Docker. We know that especially HPC centers, are very reluctant to use the Docker, and ours as well. Okay, so our benchmark center never wanted to implement Docker, so we got Singularity running. So yeah, and so every idea that we have here, model training scripts, we have deep learning, machine learning, HPC, we have pre-trained models, all the model zoos. You can download them as containers. We have all these industry workflows. I mentioned Clara, I mentioned intelligent video analytics, and so on and so on. Everything that we want to productize somehow, we package it in a container and we put it on the NGC. NGC is accessible. You just create an account on NGC and you have access to all the containers. They are for free. And not only they're for free, but they're also tested. Okay? Whenever we put a container, so for example PyTorch, the latest container, is tested that it works, and so on and so on. If you don't get it run on your problem, then you can contact us. Okay? So normally we certify that they're tested and that they run well. Here is a little bit of the list now. Yeah, here for HPC we have NumDig, Romax, and so on and so on, ParaView, and so on and so on, Café, of course, and so on. So everything that is thinkable as a product, we package it as a container. Okay, ngc.nvidia.com. Okay, now we come to the end. Thank you very much, and if you have any questions, don't hesitate. Gunter R, so with a double R, at nvidia.com. Thank you.